Weak to strong generalization via direct on-policy distillation by researchers from Tsinghua University and ByteDance.
Yeah.
The core insight here completely reframes how we scale reasoning models. So for the technical crowd tuning into this AI paper slop deep dive into the source material, here is the bottom line.
Right, the TLDR.
Exactly. Reinforcement learning with verifiable rewards, or RLVR, is incredible for boosting LLM reasoning, but it is just becoming mathematically and financially bottlenecked by the cost of rollouts on massive models.
Oh, absolutely. It's a huge issue.
So this paper introduces Direct-OPD. It's a method that runs cheap RL on a tiny model, extracts the pure policy shift, the delta between the pre-RL and post-RL states, and maps that as an implicit dense reward onto a much larger, stronger student model.
And the result is honestly staggering.
It really is. They took a Qwen 3 1.7b model and boosted it by a massive +% on the AIME 2024 map benchmark in just 4 hours, using only 8 A100 GPUs.
Which is wild.
Right. They have essentially proven that RL outcomes can be transferred as raw reward signals, not just as final checkpoints.
Yeah, and to truly appreciate why saving hundreds of GPU hours is a fundamental breakthrough for anyone managing a compute budget, you really have to look at the failure mode of the traditional alternative.
Right. Standard on-policy distillation.
Exactly. The industry has known for a while that running RL directly on frontier models is just, well, it's becoming totally unsustainable.
Because of the rollout costs.
Yes. Every single gradient update in RLVR requires the current policy to generate long trajectories, get those trajectories verified against a definitive outcome like checking if a Python script runs or a math proof is correct, and then update the weights.
Which takes forever on a big model.
Exactly. When your target model is 32 billion or 70 billion parameters, the inference cost just to generate that training data during the RL loop absolutely dominates your entire pipeline.
So the natural workaround researchers have gravitated toward is standard on-policy distillation, or, vanilla OPD.
Yeah, the intuitive fix.
Right. You run your expensive iterative reinforcement learning on a cheap 1.5 billion parameter model until it gets reasonably good at reasoning.
Makes sense so far.
And then you just take your big 7 billion parameter model and force it to copy the small one. You let the 7B sample its own states and minimize the sequence-level KL divergence to match the 1.5B teacher.
That is the standard playbook, yeah. You are essentially telling the large model, whenever you generate a token, look at what the post-RL small model would have done and make your probability distribution match theirs.
But there's a catch.
A massive one. For complex reasoning tasks, this completely breaks down the moment your student model is already smarter than your teacher model.
Which conceptually makes perfect sense. I mean, think about it like a college math major trying to learn a new trick by strictly copying a middle schooler's test paper.
That's a great analogy.
Let's say that middle schooler had a great tutor, which, represents our RL run, and they learned one brilliant, highly optimized shortcut for solving a specific type of equation.
Yeah.
If you force the college student to copy their entire paper, the college student doesn't just copy the brilliant shortcut. They're also forced to copy the middle schooler's basic arithmetic errors, their limited vocabulary, and just their overall lower capacity.
Exactly. You are anchoring the strong student down to the weak student's ceiling.
But, surely a 7 billion parameter model doesn't just forget how to do math when exposed to a weaker model, right? I'd love to ground this in the paper's actual data.
It absolutely does, and the degradation is severe. The authors mapped this out empirically using the R1 distill 7B model.
Okay, what were the numbers?
So before any distillation, this 7B model starts with an AIME 2024 score of 56.7. Then they introduce a small teacher, the Just RL 1.5B model.
Got it.
This small model has gone through RL, and its post-RL AA score is 51.3.
So right out of the gate, the student is about 5 points smarter than the teacher.
Exactly. And when they run vanilla OPD, forcing the 7B model to blindly imitate the 1.5B post-RL model, the 7B model's performance doesn't just stagnate.
Let me guess, it drops.
It drops down to roughly 50.
Wow. Wait, really? It actively overwrites its own strong baseline reasoning behavior just to conform to the weak model's capacity limitations.
Yeah, it's a catastrophic regression. The small model's RL run definitely contains a highly useful supervision signal, like it learned something valuable. But the small model's final absolute policy is a terrible carrier for that signal.
Which means we need a way to extract the brilliant shortcut without forcing the college student to copy the bad arithmetic.
Precisely.
So if copying the final model is disastrous, how exactly do the authors surgically isolate just the improvement? I mean, how do they mine this policy shift without taking on the small model's baggage?
They isolate the supervision by contrasting the weak model against itself. It is actually a very elegant mathematical formulation.
Walk me through the math.
So they calculate the teacher policy shift by taking the log probability of the new smart post-RL teacher, and they literally just subtract the log probability of the original pre-RL reference model.
Oh, interesting.
Yeah, by doing this subtraction in log space, they are entirely discarding whatever baseline preferences the weak model already had before it underwent RL.
Leaving only the delta.
Right. The only thing left, the delta, is purely what the reinforcement learning changed.
So if a specific reasoning token was heavily encouraged by the RL process, this log ratio will be highly positive. And if the RL suppressed a token, it will be negative.
Exactly, you've got it.
And for anyone working on alignment, this is where the paper stops being just a clever heuristic and becomes mathematically rigorous. Under a KL regularized RL objective, this policy shift, this simple log ratio, is mathematically equivalent to the reward that trained the weak model in the first place. Well, up to a positive scale and per prompt constant.
Spot on. It's the exact same identity that makes direct preference optimization, or DPO, function. But instead of using that math to skip a reward model, they are using it in reverse. They are treating the post-RL small model as the optimized state of some latent reward, anchored at the pre-RL reference. The pair of checkpoints literally stores the RL supervision signal perfectly in policy space.
That's brilliant.
Yeah, they extract this dense signal and apply it directly to the student's own on-policy states. There is no need to train an explicit reward model and no need to run a sparse reward PPO algorithm on the massive target model. They just use this extracted, weightless policy shift.
Wait, I have a crucial implementation question here. There seems to be a massive hole in that logic when you think about deployment.
Okay, what is it?
If the 7B student is generating its own on-policy text, it's going to explore state spaces and write complex reasoning traces that the 1.5B model never would have generated.
That's true.
Its vocabulary is richer, its logic trees are deeper. How does a student apply a reward derived from a teacher that might have generated completely different text? You can't compare log probabilities if the small teacher never visited those specific tokens.
That is the exact challenge of off-distribution evaluation, and their solution is a highly localized estimator.
Oh, the top K thing.
Yes. During training, at each prefix that the 7B student visits, the system does not ask the teacher to evaluate the entire vocabulary. Instead, it looks only at the student's top K support.
I see.
It takes the specific high-probability candidate tokens the student is actually considering for its next step, and it queries the 1.5B teacher pair solely on those specific candidates.
So it forces the small teacher to essentially grade a multiple choice question written by the student.
Yes, it's exactly what it does.
The student generates the prefix and says, based on my superior 7B parameter logic, here are the top 16 tokens I might output next, options A through P. And the system calculates the teacher policy shift, the log ratio, just on those 16 tokens to tell the scan which of its own ideas is the best.
That perfectly encapsulates the mechanism. Because they already have the full top K probabilities from the student, they can calculate the expected reward over that restricted distribution analytically.
So it's not just a random sample.
No, in statistical terms, this is a Rao-Blackwellized per-step estimator. Instead of randomly sampling one token and hoping it is a good representation of the gradient, which, creates a ton of variance, calculating the expectation over this restricted top K distribution radically reduces the variance of the gradient estimate.
And to ensure the math holds together as a valid policy gradient, they detach this weighted reward into a static stop gradient coefficient, right? Meaning no sparse reward RL on the target is needed at all.
Correct. The student explores its own optimal path, guided only by the directional nudges of the teacher's policy shift.
Well, let's pivot to the raw GPU metrics.
Yeah.
Because the mathematical mechanism is brilliant. But for the engineers grinding through this deep dive into the source material with us, they need to see why this matters for their compute budget.
Oh, the empirical results are a massive validation of the theory.
I mean, we know vanilla OPD failed. What happens when we apply this direct OPD to those same models?
They successfully used this method to improve students that were already much stronger than the teacher. Remember that Quinn 3-4B model?
Yeah.
It started at an AIME 2024 score of 72.5. They applied the policy shift from the just RL 1.5B teacher pair. Now, the teacher itself only scores around 51.
Right.
But the extracted shift boosted the Quinn 3-4B model from 72.5 up to 77.6.
That's a huge jump. It pulled an incredibly high-quality directional gradient out of a significantly weaker model. But what about beating Direct-RL? If I have a massive compute cluster, why shouldn't I just bite the bullet and run Direct-RL on my 7B model?
They ran a strict compute-matched comparison using the R1 Distill 7B model to answer exactly that. If you want to run Direct-RL on that 7B model using 32 A100 GPUs, it takes approximately 320 hours to reach convergence.
Ouch. That is a massive compute sink.
Exactly. Now look at the weak to strong route using Direct-OPD. First, you spend about 160 hours running 1,500 RL steps on the tiny 1.5B model using the same 32 A100.
Okay, so baking the reasoning improvements into the small model.
Yes. Then you run the Direct-OPD transfer stage to map that shift into the 7B model. That transfer stage takes just 4 hours on 8 A100 GPUs.
So you are basically having the overall compute time. You go from 320 hours down to roughly 164 hours.
Not only does it have the compute, it actually achieves a higher AIME 2025 score than the Direct-RL run.
Wait, really? It's better than doing it directly.
Yeah, the weak to strong transfer is faster, cheaper, and produces a more capable final model. The RL environment on the small model is vastly more stable, which allows for much more efficient exploration of the reward landscape compared to forcing a massive model to stumble around.
Okay, I have to play devil's advocate here, though.
Go for it.
Is this just an artifact of the JustRL training pipeline being highly compatible with the Quinn or R1 families? I mean, if the teacher and student share similar tokenizers or pre-training data, of course the transfer will be efficient. What happens if you use completely unrelated models?
The authors anticipated that exact critique, and the data clearly refutes the idea of this being a localized pipeline artifact.
Yes, sir.
They tested a completely different teacher pair, a Nematron 1.5B model that was post-trained using the Quest-A pipeline. This utilizes entirely different training data and recipes from the JustRL runs.
Okay.
They took that Quest and Nematron policy shift and transferred it into both the Qwen 3 1.7B and the R1 Distill 7B models.
Yeah.
The results were just as definitive. Qwen 3 1.7B jumped by plus 10.7 points on AIME 2024, and R1 Distill 7B gained about 5 points.
Wow.
The policy shift truly acts as a universal mathematical improvement direction, completely agnostic to the underlying model architecture.
If the shift is mathematically isolated and entirely independent of the pipeline, seeing that a shift can be transferred across families naturally leads to the question of whether multiple shifts can be stacked sequentially.
Oh, they absolutely can be stacked. The authors proved this in RQ3.
Walk me through the experiment.
So they took the base Qwen 3 1.7D model, which started at an AIME 2024 score of 48.3. First, they applied the JustRL policy shift we talked about earlier. The model jumped to a 58.3.
Nice 10-point game.
But they didn't stop there. They took that new, improved checkpoint and directly continued training by applying the completely separate Quest-A policy shift on top of it.
What was the result?
The model jumped again. After the second stage, it hit an AIME score of 63.8. That is a total cumulative jump of plus 15.5 points.
That's incredible. It's literally like downloading distinct skill cartridges into a robotic system. You can download the JustRL update and then stack the Quest-A update on top without the model forgetting the first update or collapsing.
Exactly. You can systematically accumulate gains learned from entirely different RL runs into a single target student.
To really trust these massive benchmark jumps, though, the technical listener needs to understand the underlying token dynamics. What is actually happening to the model's distributions under the hood?
That leads to one of the most revealing diagnostic findings in the paper. Standard vanilla OPD requires the student and teacher to have a very high top token overlap.
Right, they need to generate similar tokens.
But Direct-OPD does not. During these cross-pattern transfers, the overlap between the student's top tokens and the post-RL teacher's top tokens remains consistently low throughout the entire training process.
Meaning the student is applying the RL direction to its own thinking patterns, not blindly imitating the teacher's exact tokens.
Exactly. And the entropy diagnostics confirm this behavior. The actor distribution remains safely controlled. It integrates the logic of the reward without abandoning its native latent space.
There is a really fascinating quirk in the methodology that I noticed regarding the training horizon. They deliberately did the Direct-OPD training using a very short 2,000 token response horizon.
Yeah, that was a crucial design choice.
Wait, if you only train it on 2,000 tokens, doesn't it just revert to its old weak behavior for tokens 2001 through 16,000 during inference?
You would logically assume that, but the surprising reality is that the short horizon training generalized beautifully across fixed 16K token rollouts at test time. The actor consistently drifted toward the post-RL teacher's preferences far beyond the 2K boundary.
That's crazy.
And what is even more counterintuitive is that when they tried to extend the training horizon to 6,000 tokens, it actually yielded worse validation scores.
Wait, worse. It dropped from what to what?
It dropped from 48.8 down to 45.6.
How does providing more supervision lead to a worse model?
It comes down to distribution shift in the teacher pair. As the sequence length extends into late prefixes, the text generated by the 7B student becomes increasingly alien to the small 1.5B teacher pair.
Because the teacher only has a 1.5B capacity.
Right. When the student generates a massive, complex reasoning chain, those late-stage signals in the teacher pair become off distribution. This creates a noisy, unreliable log ratio.
So you're basically forcing the student to ingest garbage noise if you use a 6K horizon.
Exactly. A 2K horizon captures the reliable, fundamental changes in the early reasoning trajectory while discarding that late-stage noise.
And because the student is autoregressive, it just naturally extrapolates that improved early-stage logic through the rest of the generation.
You got it.
There is one final technical hurdle to making this work seamlessly in practice, which leads into the paper's adaptive KL controller. We're taking a dense reward from a teacher and applying it to a student, which creates a scale mismatch, right?
Yes, this is a critical engineering detail. The dense reward we are transferring, that log ratio from the teacher, carries a fixed scale based on the teacher's original RL budget, specifically the unobservable beta penalty.
Right.
But meanwhile, the student model uses its own KL penalty, alpha, to anchor to its initialization. Because these scales don't natively talk to each other, a fixed KL penalty fails to transfer robustly across different model pairs.
So nobody wants to spend a week doing grid search sweeps for a 7B model. How did they fix it?
The authors build a lightweight controller. At each training iteration, the controller looks at the batch level sign of the student-weighted shift.
Okay, so just checking if it's positive or negative.
Exactly. If the average shift over the visited prefixes is positive, it raises the KL penalty to prevent overamplification. If it's negative, it lowers it.
Oh, that's clever. It acts like an auto-thermostat for learning. If the student drifts into a weird state space where the teacher reference log ratio is just spitting out loud noise, the adaptive KL pulls the dense token reward back towards 0, ensuring balanced learning.
Exactly. It empirically forces the mean reward into a balanced regime without an engineer having to manually babysit the training run.
If Direct-OPD proves that an RL improvement can be isolated into a pure mathematical policy shift and applied losslessly across entirely different model architectures, what does that mean for the future of open source AI? We might stop sharing multi-gigabyte model weights entirely and instead just share the distilled shifts, the pure, weightless essence of a new capability for developers to patch directly onto whatever base model they prefer.